In problem 6.4, we are going to use Desmos to help us graph two very similar looking polynomials, and we're going to try to figure out how are their graphs different and how are their graphs the same. So I'm going to hop over to Desmos here, and they're going to tell us first of all to graph these with this window, x going from -10 to 10 and y going from -100 to 100. So that's the first thing I will set up on Desmos by going over to this wrench and changing the axis options. So x, I still want to go from -10 to 10, but y, I want to go from -100 to +100. So now our graph is set up the way they have asked us to. And we can go ahead and we can type in those two functions. So the first one, x minus 2, x plus 3, x minus 7. And let's type that in exactly as it was on the paper, and there is our function. Oh, of course I got the colors switched. Change that to red. And our next function is exactly the same except that it has this 1/2 out front. So let's go ahead and graph that one. So that's 1/2 times x minus 2 times x plus 3 times x minus 7. So there are our two functions that we're dealing with. And we've got the window they asked us to use, the -10 to 10, -100 to 100. So they want to say how are these graphs similar and how are they different? Well, first of all, what I noticed right off the bat is that both graphs have the same x-intercepts, -3, 0, 2, 0, and 7, 0. So I'm going to write that down on our paper here. They have the same x-intercepts. And I think that actually kind of makes sense because if we look at what we are graphing, those x-intercepts come from these factors, right? X minus 2, well, that equals 0 if we plug in +2. That's why we have an x-intercept of 2, 0. X plus 3 equals 0 if we plug in -3. So that's why we have an x-intercept of -3, 0. Same thing for x minus 7. That gives us our x-intercept of 7, 0. The second function has the same factors. The only difference for the second function is it has this 1/2 out front. So what is that 1/2 doing to our graph? It looks to me like it is just shrinking it. So instead of being as tall as the red graph is, the blue graph is about half as tall, it looks like. Right? This one only goes up to 24 at that peak there, whereas this one goes up to about 48 at that peak. So yeah, it's about exactly half as tall. So I can also do the same thing on the other peak here. This one goes down to -48. This one only goes down to -24. So the blue graph, they have the same x-intercepts, but the blue graph is about half as tall. And actually, we don't even really have to say about. It's half as tall. We checked some points. It is half as tall everywhere. Okay. Now, what degree do these polynomials have? So they want us to rewrite these in standard form to check, but we can make a really quick estimate here, or not an estimate, but we can make a really quick calculation to figure it out immediately. This is x times x times x, so the degree is going to be 3, because x times x times x is going to give us x to the third. But let's just make sure that works out when I actually distribute everything here. So first, let's go ahead. X minus 2 and x plus 3. They give us x squared minus 2x plus 3x minus 6. Those combine to give us x squared plus 1x minus 6. Now remember, I still have that times x minus 7. So now I've got to do another multiplication problem here. Oop, that's not going to work. Another multiplication problem. This one has 3 boxes on this side and 2 boxes on this side. So we can go ahead and do this multiplication. This is x to the third. This is x squared. This is negative 6x. And then down here, this is negative 7x squared. This is negative 7x. And this is positive 42. So now we can go ahead. There are some like terms to combine here. These are both x squared. These are both x. So we end up with x to the third minus 6x squared. And then these combine to give us minus 13x. And that last piece is plus 42. So there is, when we multiply everything out, that is what we end up with for the first polynomial, for f of x. It's just written in standard form instead. Now, for g of x, that multiplication is all exactly the same, except that it has that 1/2 out front still. But everything else did not change. So if I want to write this perfectly out in standard form, I can just distribute that 1/2. So that's 1/2 x to the third minus, let's see, half of 6 is 3. So 1/2 times negative 6x squared is negative 3x squared. 1/2 times negative 13, I'm just going to leave that as a fraction. It's 13 halves x. And then 1/2 times 42 is 21. So by just distributing that 1/2 to each of those pieces, we can find out what g of x is. And they are both degree 3 polynomials like we thought they would be. They both have x cubed as their highest power. Okay, last one up. So they want us to think about, what does this graph look like? The first thing I notice is, hey, the x plus 3, that matches perfectly. The x minus 7, that matches perfectly with the previous graphs. The 3x minus 6, though, is a little bit different. But here's a little trick we can look at. 3x minus 6 is really just 3 times x minus 2, right? Because 3 times x would give me 3x. 3 times negative 2 would give me negative 6. So that actually matches perfectly now, because there's my x minus 2. So let's rewrite this polynomial. H of x equals 3 times x minus 2 times x plus 3 times x minus 7. And we saw this before with quadratics as well. If we have that number out front, this is going to make the graph taller. It's going to stretch the graph taller, specifically 3 times as tall. Just like the 1/2 made it half as tall, the 3 is going to make it 3 times as tall as the original. So let's check that out on Desmos real fast. If I take that same function that we started with, and now I just throw a 3 out front, well, boom, there's our graph that is 3 times as tall as the original red graph. And again, you can check some of those peaks, and that is 3 times taller than the original red graph was. So, went through a lot there to check out those 3 different functions. A lot of multiplying, a little bit of factoring, but that is how that number out front, right, that leading factor, that number that's multiplying through by everything, that is how that affects these graphs here.